So we know an AI model's goal is to minimize its error, and we know the loss function acts as its scorecard, telling it how wrong it is. But that leaves a gap. How does the model use that score to actually get better? How does it adjust its own internal workings step by step to find the right answer? This is the core of the training process. It's not a flash of insight, it's a methodical, relentless process of improvement. The most common engine that drives this improvement, and quite a good demonstrator of the types of processes involved, is an algorithm called gradient descent. The easiest way to understand gradient descent is with an analogy, I think. Imagine you're standing on a vast hilly landscape in the middle of a thick fog. Your goal is to get to the absolute lowest point in the valley, but you can only see the ground a few feet around you. What's your strategy? You'd probably feel the ground around you, find the direction of the steepest slope downhill, and then take a single step in that direction. From your new position, you'd repeat that process, find the steepest way down, take another step. You keep doing this step by step until you can no longer find a way down, and at that point you assume that you've reached the bottom. This is the essence of gradient descent. The hilly landscape is the error landscape created by the loss function, where height represents the size of the model's error. The bottom of the valley is the point of minimum error, the best possible performance. The gradient is just a mathematical term for the steepness of the direction of the slope, and the descent is the model taking a step downhill to a point of slightly lower error. The model calculates the gradient and takes a small step in the opposite direction, adjusting its internal parameters to improve its prediction. It does this over and over millions of times. Now, the size of each step the model takes is a critical setting called the learning rate. In our analogy, if it's a tiny shuffle or a giant leap. If the steps are too large, you might leap over the bottom of the valley and end up on the other side. If they're too small, it can take an impractically long time to get to the bottom. So why is this all important for clinicians? Understanding gradient descent demystifies the training process a bit. It shows that an AI learning isn't magic, it's an iterative, methodical search for the best solution. So this in part explains why training AI models is so computationally expensive and time-consuming. The step-by-step process repeated for vast datasets is what requires all that processing power that you hear about. It's also helpful to introduce and understand the concept of a learning rate mentioned in the methods sections of most papers. You know what it is. It's one of the most important hyperparameters, which we'll come to shortly, that precise term, but it's set by researchers in the model that they're training. Their choice of learning rate directly impacts how well or even if the model finds an optimal solution. A poorly chosen rate can lead to a suboptimal model, no matter how good the data is. So that's gradient descent and learning rates in a nutshell. It's the simple, powerful engine that allows a model to navigate its way down the landscape of error one step at a time to find the best possible answer.